Okay, let's continue. So remember the censoring data example. We have this likelihood, right? The exponential distribution, and so the MLE can be taken by take the partial derivative, which is the scope function. The scope function of the scope function is this one, which is actually 1 over theta delta I minus yi. So if you set it to 0, then you have this one as the MLE. Now, to compute the Fisher information, you take the partial differentiation again, right, with respect to, so information theta and minus, you get theta square delta I. This is your observed Fisher information. And then you take this is random variable. And then your expected Fisher information is essentially, you take the expectation of delta I, right? So the expectation of delta I, you get this. Okay. So then now you are interested in estimating the variance. So suppose you are interested in estimating the variance. You have two choices. One is you just use the observed Fisher information and plug it. The other option is you compute the expected Fisher information and plug in, right? So you have two different choices. This one and this one. And which one do you prefer? So that is the question. The short answer is that this one is better. The observed Fisher information is better than using the expected Fisher information to evaluate the to compute the to evaluate the uncertainty associated with the MLE. Why? Why? Because, okay, here's some. So this is, we know this is MLE, right? And you are interested in computing the MLE, variance of the MLE, estimating the variance of MLE. Now, suppose that, for example, suppose that your data, right, your censoring data didn't have any censoring. Suppose. Okay. So if you don't have any censoring, no censoring, then your MLE is just this one, right? Because delta equal to or equal to 1. Then you may wonder, how should I evaluate? So basically, because this expected Fisher information is taking the average, taking the expectation of all possible delta, right, in the distribution. So from the mechanism. So then you are actually averaging out over the possibility that is censored or non-censored. You take the average. While this guy, right, this guy, so if you, in this case, your Fisher information will be just, you have n divided by theta hat square, because we that all delta equal to 1. So in this case, we know it recognizes. So it recognizes that there's no censoring in the data. And so it makes more sense to reflect the realized event rather than take the average of all possible, possibility. And so So that is why observed feature information is regarded as better measure for computing the variance of the MLE. Okay, so that is the goal. And so and now the problem is usually computing the information, feature information requires computing the mean score function, right? The partial derivative mean score function. And remember, you know, the beauty of a mean score theorem is what? We avoid, right? We avoid computing the marginal density, the observed likelihood. So mean score theorem is interested in computing the scope function, observed scope function, by computing the conditional expectation of the right. So okay. So the mean score theorem is to use the complete sample scope function and then take the conditional expectation. Right. That is the whole idea of the mean score theorem. We use this one as and show that this is the observed information, observed scope function. And so natural question is, can we have this kind of a nice result for information matrix? So question is how to express this guy in terms using the, so this is usually easy to get, right? This is easy to get or known. So they are already known. And now question is there any way we can compute the information using this complete sample information and complete sample scope function? And that has been investigated. So Thomas Ruiz, okay. Thomas Ruiz. You know, we don't need many papers to be famous, just one. Okay. So one paper can make you famous. And for Thomas Ruiz, this is the most famous paper. I'm sure he published a lot of other papers too, but this make him famous. So and then people call it Ruiz formula, right? So then if you somebody if I can make Kim's formula, that would be nice, right? So anyway, this is called the Ruiz formula, and basically he derived the form of the observed information using the complete sample feature information only. Okay, so this is, remember, this is what? This guy, right? This guy is this guy. So at end of the day, he get this formula. Okay, he obtained this formula. Okay, let's first understand what is the meaning of this formula. So let's use the same example 2.3, which is the censoring data. So I hope this is recording. Okay, so this, we know this is the scope function under the observation of TI, and this is the feature information. So that's given, known. And now the formula here for equation 4. So so the first part is even easy, right? You don't have any random variables. So this is already known. So this part is n divided by zeta squared. The only thing you need to compute is this guy. And so we want to do that. And so this is what we want to compute. And so T is random. So the variance is this. And this is exponential distribution. So exponential distribution, the variance, I mean, it's memory is property, so variance is just this one. So end of the day, you get n divided by zeta square, and this guy, right? So that you get this. So that is what? That is equal to what we already here, right? So we have this formula already. Where did we get this formula? We computed this formula directly from differentiating the observed likelihood, observed scope function. Okay. So we know, so that means that matches, so this result matches with what we know. So it's no script I, that we know that we computed from the zeta, okay, log L obs zeta. Okay. So that confirms our theory. Now, how to prove it? This, so the proof. So the other guy is in Israel, I think. So oak, the formula. So the proof for oak is easier. So I use the oak's approach. So we should to compute what I obs eta equal to, so let's assume scalar. So it's not really, so we need a more complex notation, but we just make life easy. And minus, right? L log s. So we wish to compute. Okay. So which is actually minus eta s observed score. Okay. So we'll use this formula. So to be rigorous, this is P minus 1 vector. So this should be transpose if you are going to talk about vector parameter. So okay. And then this one is what? Ascom eta given data. So I'm going to use just the data to denote y obvious and eta delta, right? This is what we have. And we this integration, so remember this expectation has a integration with respect to density function, which is y means given y obs and delta evaluated eta. So one thing I like to emphasize is that it's a function of, so eta takes place in two places. So the original eta in SCOM, and then the eta here is in evaluating the expectation, conditional expectation. So you need to apply the chain rule to rigorously apply the this differentiation. So that is, you first need to come data plus you second, right? So this is the first one, and second one, you need to probably use the definition of integration to clearly state what is going on. So we want to compute the partial derivative over the density function with respect to the y miss. Okay. So the first part, we know that this is expectation condition minus of the conditional expectation of the icon given data. So the first part is no problem. The second part, so we need more space. So let's write it more carefully. So Scom eta. So the density, partial derivative of the density is always equal to the scope function times the density, right? So remember, okay. So question is how to write, how do we, so for example, why? What is this one? Well, this one is a scope function derived from this log f from f, and then this f. So this, why? Because this guy is log f, right? So remember, if you take the partial differentiation with respect to eta on log f, then you have a numerator in f and denominator f prime. And so denominator f and this f cancels to each other. So that's what is going on. So we use that, right? So this holds for any general f. So so that means this particular, we use this particular f, which is the miss. Then you have S miss, and then the density is Y miss given Y obvious and delta and eta. Okay. So that makes this stop equal to S com eta times S miss. So you have a prime, so that actually gives a eta prime. Okay. Something like that. So something like this. Okay. Okay. So that means you have a conditional expectation of the SCOM eta S miss eta prime, and then given Y given data. And then you use the formula as decomposition obvious eta plus S miss eta, right? So you use this decomposition. Let's use the well, let me try to simplify a little bit. So remember, this one is S obvious eta plus S miss, okay? And then you basically, that means you have a S obvious eta times S miss eta prime given data and eta plus expectation of S miss eta S miss prime eta given data. The first term is 0. Why? Because we know we talked about the orthogonality, right? As obvious, missing part and observed part are orthogonal score function. So the first term is 0, and so second term, only second term remains. That is actually, so that is what? This is actually conditional variance. That is actually conditional. That's what I think that's what this guy, right? One thing I haven't. So then, so this guy is S. Okay. Sorry. Let me. Okay. So that means you have a S miss eta given data, and then another way of saying this is you have observation eta given data and conditional on data. This is a constant, nothing random. So that means you can even write it as com eta given data. Okay, that is, so that is this guy. Okay. So that means we have eventually this means that we end up computing this guy is equal to variance of the conditional variance as com given data. Okay. This guy. Okay. And then the end of the day we simplify. So that we take the negative, right? So because this one is because this guy is a negative minus of the as obvious eta. So we should take the negative value, so that gives equation form. So that proves our result. So result 4 is closely related to missing information principle. And I think I already covered this. So basically, you have first equality is just variance is expectation of variance and variance of expectation, and then this guy is 0. So then you get this one, and then from here, third equality, you originally you have a minus as obvious here, but this is constant. So you can safely ignore in the competition. So okay. So what is the Lewis formula is important in evaluating the variance of the MLE on the missing data. And if you remember when you look at this conditional on data, right? You're computing the so basically we use y miss given y obvious and delta to evaluate this conditional expectation and conditional variance. So that is a prediction model. Sometimes we can call it imputation model. So basically we later we'll learn that the Lewis formula is closely related to computing the uncertainty using imputation. So okay, I think that's all for the Tuesday class, and I'll look forward to see you on Thursday. Thank you.